Okay, so welcome everybody. So today we have a PhD seminar by Moshe Shienman. So Moshe completed his BSc degree in computer science with the Technion in 2013, and he's been pursuing his PhD degree in a direct track PhD degree in TASP since 2019. Okay, go ahead, Moshe.
Thank you, Vadim, for that introduction. And hi, everyone. My name is Moshe Shienman, and today I will present my PhD seminar, Structure-Aware Probabilistic Inference and Belief-Based Planning with Performance Guarantees, which summarizes my research work in the past 6 years or so under the supervision of Associate Professor Vadim. So beginning with a brief introduction, we find ourselves in an era where intelligent autonomous agents and robots are increasingly incorporated in our lives and everyday activities, from robotic surgery to autonomous vehicles and drones. Yet to fully integrate these autonomous agents into our lives, we first want to make sure that they are doing what we expect them to do. And specifically, we require that these autonomous agents would operate both reliably and efficiently in the real world. And operating in this real world environment is not easy. These agents need to be able to handle different sources of uncertainty, such as noisy measurements, as physical sensors are not perfect, imprecise actions, when a robot tries to take some action, but for some reason the result is not as expected, and maybe dynamic environments in which unexpected events can occur. And so dealing with such uncertainties, a truly autonomous agent should be able to perform both inference, meaning it should reason over high-dimensional probabilistic states known as beliefs, given available information. And he also should do decision-making uncertainty, which is also known as belief-based planning, where it should autonomously determine its next best actions while reasoning about future belief evolutions. And when solving these two problems, it is common to discretize time based on the interaction of the agent with the environment. Where in each time step K, the agent can take a specific action, which we denote by UK, and the agent can acquire a specific observation, which we denote by ZK. Now, these observations, they can either come from onboard sensors, such as cameras or lidars, but it can also come from external sensors, such as GPS. And in terms of notations, in each time step K, we have a random variable xk, which denotes... Sorry? Sorry.
Go ahead.
So in terms of the notations, in each time step K, we have a random variable xk, which denotes the state of the agent and or of the environment. This can represent, for example, position and orientation. Capital XK denotes the joint state from time step 0 until the current time step. We also assume we are given some probabilistic motion and observation models. Those are usually modeled with some Gaussian noise. For example, given the current state of the agent at time K and at the action. Can you just mute everyone, your mic? Thank you. So, for example, given the current state of the agent at time K and a specific action, the random variable representing the state at the next time step, xk plus 1, is then given by the motion model with some Gaussian noise term wk. And given all actions and observations from time step 0 to the current time step k, we get a posterior probability density function over the joint state, which is also called the belief, and we denote it by bx of k. Okay, so as we said, first task that the agent should be able to do is probabilistic inference. And while maintaining a probability distribution, there is in fact a true state for the agent in the environment. And this true state is commonly recovered by the map estimate, meaning we need to look for the specific assignment X star that maximizes the probability function. And in the nonlinear Gaussian case, meaning when the models are given with some Gaussian noise, this problem is basically a nonlinear least square problem, which is commonly solved with nonlinear optimization methods such as Gauss-Newton. Now, in these nonlinear optimization methods, a linear least square problem is solved in each iteration. And without diving into technical details, each equation contains a rectangular matrix A, which contains all these non-zero blocks denoted in blue, which represents the Jacobian of all measurements with respect to the variables. And when solving this equation, we recover the pseudo-inverse by multiplying A transpose A, which is also known as the information matrix or the inverse of the covariance matrix. And these matrices are widely used as they actually contain information about the uncertainty of the entire estimation problem. Now, the second task that the agent should do, as we said, is belief space planning. And in belief space planning, the agent should be able to determine in each step what is the optimal action or set of action it should take with respect to some objective function. This could be, for example, distance to go. Now, for every action that the agent takes, it is common to associate some cost or reward, which we denote by C. And this cost function, written here first in general, can be either state-dependent or belief-dependent. And looking for the optimal action, we need to evaluate the objective function for every possible action or set of actions. However, as we don't know which observation we might encounter in the future, we theoretically need to consider every possible observation and take the expectation of that cost function with respect to every possible observation. Now, notice that for evaluating the cost function in future steps, we need to be able to access the belief or the state. And for that, we need to also do inference. So planning into the future also involves inferring future belief evolutions. These two tasks, inference and belief space planning, are computationally very hard, especially in high-dimensional state spaces. And it becomes even more challenging when the agent has to operate in real time in the real world, often using inexpensive hardware with some limited compute resources. So for that end, we need to come up with ways to reduce that computational complexity. And this leads us to my research goal, which is to leverage different structures and solve computationally simpler problems that are related to the original problem while providing some guarantees. These structures that I'm talking about can be topological structures associated with a graph representation of the problem, and it can also be specific structures of the underlying belief distributions. So what are these simpler problems? Imagine we have a computationally very hard problem, a very hard planning problem. Our goal is to find an alternative problem with respect to the same set of candidate actions that would ideally be, one, less expensive, obviously, to compute. Two, it should discriminate between candidate actions, meaning it should tell us which actions are better. And three, it would ideally find the best action to take as the original problem. Now, the way that we do that is by bounding the objective function with functions which are easier to compute. For example, in this figure, action U3 minimizes the original objective function denoted by this orange line. And if a simpler upper bound denoted by blue line for U3 is smaller than all of the lower bounds denoted by the black line, we will be guaranteed to select the best optimal action. And when this happens, we call that action consistency. So with that, we start with my first published work. This is called Focused Topological Belief Space Planning, which is a joint work with Dr. Andrei Kitanov and Professor Vadim Inderman. This work was published in 2021 IEEE RAL and ICRA. And in this work, we try to leverage topological signatures of graphical models to solve a simplified problem and reduce that computational complexity. And before we talk about the topological signatures, let's first present the concept of factographs. So factographs are probabilistic bipartite graphical models with two types of nodes. We have the variable nodes that represents the random variables in our estimation problem. And we have the factor nodes that represent the probabilistic information on those variables. Now, a factor graph represents a factorization of the joint belief. So in the small example, if the joint posterior belief is equal to some normalizer times some prior distribution over x1 times the distribution over, or distributions over x2 and x3 given by the motion models and the actions, it is in fact proportional to the product of all the factors in the factor graph. And as a motivation for leveraging topological structures of such a graph image, of such a graph, imagine that if you have an estimation problem, you would ideally want to have more measurements to achieve better and more accurate results. Now, the more measurements you have, the more edges the corresponding graph will have. In this figure, for example, we see a robot navigating to a goal position, and it can choose between path A2, where it will have where we do not have actually any loop closure measurements, and the corresponding graph topology will be, or will have a chain-like structure, and the uncertainty will grow with time. Or on the other hand, it can choose path A1, where there are free loop closure measurements that reduce uncertainty. So maybe there is some connection between the topology of the graph and the quality of the solution. So given a factor graph, which corresponds to an estimation problem, we first know that, as we already saw, when solving such an estimation problem, we have the information matrix, which encompasses the amount of uncertainty in the system. On the other hand, each factor graph also induces a topological graph, and this topological graph in graph theory has what is called the Laplacian matrix. Now, that Laplacian matrix describes the connectivity of the nodes in the graph, and it also has a specific signature given by Kirchhoff's theorem, which is the number of spanning trees that we can break this graph into. Now, this signature is directly associated with the determinant of this Laplacian matrix. And so around 2015, a paper was published by Kasra-Kosusi where he identified these Laplacian-like structures in the information matrix, which is associated with the estimation problem, and he used that to bound the determinant of the information matrix. So now we have a direct connection between a topological structure, which is much easier to compute, and a quantity that tells us something about the uncertainty of the system. In 2018, Dr. Tanov and Professor Lindelman used these signatures for the first time in belief space planning problems. In this work, we tackle the focus case. Unlike the unfocused case, where the objective function considers all variables within the estimation problem, in a focused belief space planning problem, the objective function prioritizes or only considers a predefined subset of focused variables. The motivation is that in different tasks, specific landmarks within the map or certain states of the robot might be more important than others. As an example, we can think of a collision avoidance task where localizing obstacles is much more important than localizing other landmarks in the environment that do not pose immediate threat of collision. A second example could be a focused reconstruction task, such as creating a 3D model, where we specifically need to recover the foundations with higher accuracy for maintenance work. Also, in general, focused and unfocused problems can have two very different optimal solutions, even when we consider the same set of candidate actions. Okay, so note that we denote such set of focus variables with X, K, capital F, and that the union of the unfocused and focused sets, where the unfocused is denoted with capital U, is equal to the entire set of variables. So our contributions in this work are as follows. We were first to consider utilizing topological aspects in a focused belief space planning problem. We also derived two topological signatures to approximate a focused cost function. And finally, we prove asymptotic convergence and develop bounds for one of these topological signatures. Specifically in this work, we considered an information theoretic cost function, which is differential entropy. And in this focus setting, we are also only considering the cost over the terminal marginal belief over focused variables at the end of the planning horizon. However, the focus set of variables can be very small with respect to the entire problem. And calculating a marginal information matrix, this lambda MF, for each candidate action becomes an expensive Schur complement operation. So after some manipulations, algorithmic manipulations, we see that the same objective at the bottom now has two terms. One that corresponds to the information matrix of the original problem, that's the determinant of lambda. And the other one that corresponds to the information matrix of the unfocused set, that's a determinant of lambda u. Now, it turns out that these two terms are actually much easier to compute. And in the paper, we present what we call the unfocused augmented graph, which allows us to efficiently calculate topological signatures of these two structures. And for more detailed information on how exactly we recover these structures, I strongly encourage you to read this paper. Based on this, we presented in the paper two topological signatures. The first is called weighted tree connectivity difference, for which we're able to analytically bound the approximation error with respect to the original problem. And a second topological signature called the von Neumann difference signature, which allows us to further reduce the computational complexity, as it does not require calculating a determinant. However, we cannot use it to bound the original function. We evaluate our approach in two real-world data sets. We start with the focused measurement selection problem, where we can see the very high correlation on the graph to the left between our two topological signatures, that's the y-axis, and the original focused objective function, which is the x-axis. That strongly suggests that the topological signatures can be used to solve this problem. We then evaluate our approach in a focused active 2D post-SLAM problem using the Intel data set, where we can again see the high correlation between our topological signatures on the y-axis and the original focused objective function on the x-axis. However, this time, as this is a planning problem, we can also see how we utilize the error bounds of our first signature, which are denoted by solid blue lines, to provide performance guarantees and maintain action consistency. In the table to the right, we see how the computational complexity is improved by an order of magnitude when solving these problems with our topological approach. So now we were wondering if, other than topological structures, can we also leverage other structures to solve simplified problems? And this led to my second published work, the Steel Data Association Belief-Based Planning with Performance Guarantees under Budget Constraints, which is a joint work with Professor Indelman. And this work was presented in ICRA 2022, which is the largest annual robotics conference in the world. And it was actually selected as one of 3 outstanding paper awards finalists, which obviously was a great honor. And in this work, we specifically addressed the real problem of ambiguity. So what is ambiguity? Ambiguity is when a certain observation can have more than one possible interpretation. For example, a slip and grip problem, where the agent thought he moved forward, but he actually stayed in the same place. It could be loop closure problems in SLAM, where the previous landmark or location was falsely identified as something else. And it can also be unresolved data association, where, for example, an agent observes a specific door, and he knows that there are 3 such doors in the map, and he fails to realize which door this is exactly. Now, all of these eventually lead to multi-model probability distributions. And these multi-model probability distributions are computationally very hard to work with in both inference and planning. So consider the following as a motivation. Assuming an agent at time k observes a bicycle, and he knows that there are 2 identical bicycles in the environment. And without any further information, now it must hold 2 hypotheses, either if it belongs to the bicycle number 1 or bicycle number 2. Now, further imagine that in the next time step, the agent observes a scooter, and again, he knows that there are 2 identical scooters in the environment. Now the number of hypotheses quickly exponentially grows to 4, making this problem even harder. And in general, if the agent starts with some initial single belief, with every ambiguous measurement it receives, which it is unable to solve somehow, the number of hypotheses keeps growing exponentially in both inference and in planning. Now, to formulate this problem, the belief at each time k is now over both discrete and continuous variables, and it is expressed as a linear combination where the probability over data association realization vectors, those are these beta vectors, which assigns specific observations to all possible interpretations. Those beta vectors serve as the hypothesis weights. So for example, if we have this association beta vector in the picture, we can either associate the first observation of a bicycle to the second one as it is depicted, but it can also account for the first bicycle within the environment. And so our contributions in this work, we show how to utilize a subset of hypotheses in planning to reduce the computational complexity. We also develop a connection between our approach and the two analytical solution. That means the one that includes all possible hypotheses, and we do that for a myopic case where we consider only one step into the future. We derive bounds based on our solution over the analytical solution and prove that they converge. And finally, we also address the challenging setting of hard budget constraints and show for the first time how these bounds provide performance guarantees. So how do we reduce computational complexity? The motivation is to only use a subset of hypotheses to evaluate the objective function to reduce complexity. In this example, if we had a belief which was constructed of three hypotheses, we only choose those two subsets or the subset of these two components, which are denoted in green, and we discard the one which is denoted in red. And we denote such a chosen subset as a simplified belief. And also notice that in a simplified belief, we had those beta vectors that we used as weights. Now we need to renormalize those selected hypothesis weights just to make sure that this is indeed a valid distribution. Now, in this paper, we also choose to look at an information theoretic cost function. However, this time, the entropy is both over the discrete and the continuous variables. So using some simple algebra, we can easily see how this is broken down into two terms. One, which is entropy over the discrete variables, representing the hypothesis weights, and a conditional entropy over the continuous variables, given a specific data association. Now, specifically, if we want to disambiguate between different hypotheses, we only need to consider that first term, which is the focus, or which is what we choose to focus on in this work. So in this paper, we show how the objective function in a myopic setting is bounded both from above and below using a simplified belief, which only considers a subset of hypotheses. Now, these bounds, they're not so intuitive, so I prefer to leave them out here, and I strongly suggest that you read the paper for more information. And just as a reminder, the way that we utilize these bounds is to provide performance guarantees with respect to the original problem, meaning with respect to considering all possible hypotheses. Okay, so we show our proposed method first in a budget-free scenario. This is a classical kidnapped robot problem where the agent is denoted, which is denoted by these black circles, initially observes one of 8 identical blue squares in the environment without knowing where it is truly located. And then he has to take actions to disambiguate between the different hypotheses. Now, this is a budget-free scenario because for a simplified belief, we start with a single hypothesis, we calculate the bounds, and then if we are unable to disambiguate between actions, we incrementally add hypotheses to our simplified belief and repeat that process until we're able to disambiguate between hypotheses. Now, we also show in the paper how we can computationally very easily incrementally update those bounds based on the hypotheses that we had. And to the left, we can see a time complexity comparison for full hypothesis disambiguation of our approach in blue versus the approach that considers all possible hypotheses in red. Now, this is as a function of the number of prior hypotheses we considered in this scenario. And we see that the more prior hypotheses we consider to begin with, the merits of our approach are more prominent. In our second experiment, we consider a budget constraint setting where the agent only has the resources to calculate the solution based on a single hypothesis. And to the left, we can see that initially the agent has two hypotheses regarding its location. Those are denoted by 1 and 2. And in the middle figure, we can see what happens when the agent only considers hypothesis number 1 in planning. The bounds, denoted by red and blue lines, are not informative, and we cannot make a good decision. Moreover, if we choose to prune the second hypothesis, as we have no budget, and that was common practice before our approach, then we can see by the black line that the agent will actually choose to go right. However, we know from the green line that one represents the solution for the original problem, considering both hypotheses, that the agent should actually go left. On the other hand, if we do planning while considering only hypothesis number 2, we see now how we can utilize the bounds, again in red and blue lines, to guarantee that we choose a solution which is consistent with the solution of the original problem. Now, through bounds, we see how we were able to achieve this action consistency rather than if we only prune based on these black lines, we were unable to show or we were unable which of these solutions we would have decided to choose. Okay, so as a quick recap of the contributions in this work, we presented a novel planning approach that utilizes only a distilled subset of hypotheses in a myopic setting. And we show how to utilize these bounds in both budget-free scenarios to reduce computational complexity while preserving action selection, and how to use these bounds under budget constraints to provide performance guarantees. And following this work, a natural extension was to consider longer planning horizons, meaning a non-myopic case, which can consider planning for more than one step into the future. And this work, non-myopic distilled data association belief space planning under budget constraints, which is also a joint work with Professor Lindemann, was presented in ISRR in 2022. And handling data association ambiguity with exponential growth in the number of hypotheses in the non-myopic case is even a greater computational challenge, because when we do planning for longer horizons, a common approach is to construct a planning tree that with each planning step branches according to every possible action and observation. So we have the exponential growth into further longer horizons. And also recall that in each such subtree or subtree node, we have to perform inference in order to consider the evolution of future beliefs. And however, constructing such a planning tree is not trivial under budget constraints, because if we have to simplify a belief at some point in some belief tree node, this has a direct effect on all of the children nodes further down the tree. Now, commonly, inference and planning and belief space planning are treated as two separate processes, and theoretically, each of these can have its own computational constraints. However, the implications on the belief tree nodes are different when we consider budget constraints in inference or in planning, or in both. So look, for example, on the planning tree to the left. In this example, there are no budget constraints in inference. And as such, the number of hypotheses, which are denoted by these blue, red, and black Gaussians, can exponentially grow, while the planning algorithm can utilize all hypotheses in planning. On the other hand, in the example to the right, where we have budget constraints in inference, and thus each tree node can only contain a subset of all of the theoretical hypotheses, and the planning algorithm can now only choose from this subset. So we see the difference in between utilizing or between having budget constraints in inference, for example. So what are the contributions that we have in this work? First, we extend our previous work to a non-myopic setting. We also derive bounds for the two analytical solution based on simplified beliefs, and we prove that these bounds converge. And finally, we thoroughly study for the first time the impacts of how these hard budget constraints have in either planning and or in inference. So similar to the myopic case, we now define a simplified belief for the non-myopic case. That's BK plus N for the non-myopic setting, simplified for S. And now we use the same cost function as in our previous work to disambiguate between hypotheses. And we derive analytical connection between the cost function when considering all possible hypotheses to only using a subset of hypotheses, which is denoted by this simplified entropy, HK plus NS for simplified. And in the paper, we show how to bound the cost function from above and below. Moreover, how these bounds converge to the two analytical solution when the simplified subset of hypotheses reaches or approaches the entire set of all possible hypotheses. And this is actually an important property, as it is not trivial that adding more hypotheses to a subset actually improves the approximation. And again, as you can see here, these bounds are not so trivial. And for more information on how we derive them, I refer that you read the paper. Also, as a reminder, we utilize these bounds in planning to decide on the optimal action with respect to the original problem. And the first experiment in the paper, again, considers a kidnapped robot scenario. Now, in this scenario, the agent is awakened in one of several identical floors. You can think about it as a hotel-like environment or a power building-like environment where all floors look very similar. And it has to take actions that would disambiguate as quickly as possible so he could understand in which floor it is located. And in this specific scenario, we consider the possibility of no budget constraints on the number of hypotheses in inference nor in planning. So same as before, we start by choosing a subset and then incrementally add components for hypothesis to that subset until we're able to disambiguate. And as you can see to the right, our approach strongly outperforms the general approach that considers all possible hypotheses, even as the number of prior hypotheses, meaning the number of different floors that are used in the simulation, is increased. And another really nice analysis done in the paper is to understand the effect of budget constraints on performance in planning. And this is a non-myopic setting. It is very difficult to disambiguate between candidate action based on bounds, as we did so far. So instead, we can bound, or if those bounds, as you can see on the image to the bottom left, if those bounds do not overlap and we cannot disambiguate between those actions based on bounds, then we can at least quantify the loss in solution quality based on the overlap of these bounds. And in this experiment, we evaluate the loss in solution quality as both a function of our budget constraints, meaning how many hypotheses we can utilize in planning, and the planning tree depth, meaning how further away into the future our planning horizon is. And we can see, this is not surprising actually, that with higher budget constraints and longer planning horizons, how our loss decreases. So after considering multi-model distributions in both inference and planning, we realized that not all real-world posterior distributions have a parametric structure. And handling such non-parametric distributions is not trivial in both inference and in planning. And this led to our latest submitted work, recently submitted to iOS 2024, which is called the Slices Perspective for Incremental Non-Parametric Inference in High-Dimensional State Spaces. This is joint work with Ohad Levio from our lab, Professor Michael Kayas, and Professor Vadim Inderman, where we set to understand how to efficiently handle non-parametric distributions, specifically in inference. And with that motivation in mind, we know that due to the complex non-Gaussian nature of such posterior distributions, obtaining closed-form analytical solutions is challenging and frequently impractical. Now note that we still assume that the motion observation models are known and given, so somehow they will learn maybe, but they are not necessarily Gaussian, which leads to non-Gaussian posterior distributions. Now, in the Gaussian case, a common approach for computing posterior distributions is what is called the forward-backward algorithm, where during the forward pass, the factor graph is gradually transformed into a base net, which represents conditional distributions. And in each step, this is an iterative process where in each step, a single variable is eliminated out from the graph, and the new factor is added in turn to define the density in the remaining variables. Now, once this forward pass is completed, the joint distribution is expressed via conditionals, and the marginal distributions are calculated using back substitution. However, in the non-parametric case, there is no closed-form solution, and this forward-backward approach is not trivial since we need to understand how to represent these new factors and marginals during elimination and backward pass. Now, there are two notable online approaches that handle the non-parametric case in high-dimensional settings. The first was presented in 2016 by Hans Fouillet, and he suggested to approximate these intermediate factors with kernel density estimations based on samples from the eliminated variables. However, notice that this approach requires a two-step approximation process where we first must sample the eliminated variables and then do another approximation using KDEs to construct these F-new factors in the elimination. And then a second approach, which was recently proposed in 2021 by Huang, where the authors suggest to learn a normalizing flow function based on samples from the eliminated variables to approximate these desired distributions. Now, notice that this is a learning process, and it can also be considered as another approximation, and it also requires some additional resources. So our key observation in this work is that since we have access to the given models, we can use what we denote as high-dimensional slices to approximate marginal distributions. Now, consider, for example, the joint distribution over two random variables, x and y. In theory, if you want to get the marginal distribution over x, we need to integrate out all possible realizations of y. In practice, we cannot do that. This is a continuous space. So given samples of y, we can access these high-dimensional slices over x, which are given by the models. And then when we sum all these slices denoted in red, we get a more direct approximation denoted in blue for the marginal distribution of x that does not require any additional approximation, nor any learning possibility. And so what are the contributions our contributions in this work? So we leverage slices from the high-dimensional surfaces structures to approximate joint and marginal posterior distributions without any further intermediate reconstructions. We suggest a novel early stopping heuristic criteria that's in the backward pass to further speed up calculations. And then finally, we show that our approach requires less samples and outperforms other methods in computational complexity. So how we utilize these slices in non-parametric inference, we use the same forward-backward algorithm. And in the forward pass, we approximate each new factor added during elimination using our slices perspective. And then in the backward pass, we also approximate those marginal distributions using our slices perspective again. And I don't want to go into details on how exactly this is done, so I refer you to read the paper for more information on how these formulas are derived. Our second contribution is that in an incremental setting, in real-world systems, we usually need to do inference whenever new data is present. However, in 2012, Professor Michael Kayas suggested in his PhD that we do not have to do inference from scratch, meaning we do not have to do the entire forward-backward algorithm from scratch each time to get new estimates, since new data sometimes does not affect variables that represents locations that are further away. And as such, he suggested an early stopping heuristics to stop the backward pass based on previous variable estimates. And he did that in the Gaussian case. Now, in this work, we extend this notion to a non-parametric high-dimensional case. However, this time, as we have a non-parametric distribution, we need some metric to quantify whether we should stop this backward pass or not. And for that, we suggested to use what is called the maximum mean discrepancy metric, which is a metric that quantifies the distance between two distributions based on samples. One of our evaluations in this work is that we evaluate an approach versus the other two approaches that we presented on a real-world data set called PLAZA, where the measurements are range measurements. Now, this setting, as it is a range measurement, and the landmark or a range or a measurement to a landmark can actually be in a 360 circle behind the current around the current location. Now, this setting creates a non-parametric posterior distribution. And as we can see in the graph, our approach in red outperforms the other two approaches in both RMSE, root mean squared error, with respect to the true location of the landmark in this scenario and the 4 landmarks that they use. And that so it outperforms both approaches in both RMSE, which represents the estimation error basically, and in computational complexity by an order of magnitude, which is, in my opinion, very impressive. Okay, so just to summarize what we had and what we've done in this research. So we leverage structures in both inference and belief space planning problems. Those were topological structures from graphs associated with the problem, and there were posterior distribution kind of structures, slices or structures. We used that to reduce computational complexity by solving simplified problems to handle real-world scenarios under budget constraints. And additionally, we provided performance guarantees in planning by bounding the error between the original, very computationally intense or hard problem and our simplified problem to provide what we call action consistency. That's it. Thank you.
Thank you, Moshe. Thanks. We have time for a few questions. If anybody wants to ask. Okay. Last chance to ask the question. Okay. So thanks, Moshe, for this interesting seminar. Thank you, and bye for now. Thank you.